Hi guys, so we have to know about the statistical metrics before going to the deep dive into the different machine learning problems of the like which we can solve using decision trees. So say for entropy, you can actually not see it. So this is entropy, and so entropy actually tells you the impurity levels of a particular decision tree. Like suppose if all the attributes or the in a branch it is A, then the entropy would be most probably here entropy of A would be 0. Okay, because like everything in the decision tree over here, the child node, parent node, grandparent node, it is mostly A. So what's the point of learning over here? So the impurity levels are 0 over here, and you can say the uncertainty or the surprise, and also like the ratio, the purity ratios over here would be 0 over here. So for example, if the impurities over here, say for example A, B, C, A, then D and A. So suppose if I take this particular branch A, B, C, D, then the impurity for entropy of A, I can actually say it like the individual entropies will be calculated. So the statistical formula for entropy is actually minus P sigma log Pi. Okay, and Pi is actually calculated by like somewhat like this. So if I want to calculate entropy of A, then entropy of A as B, C, D. So I have to, and there are 4 samples in this particular data set. So I will be actually taking entropy of B, entropy of C, entropy of D. And so it will obviously not be 0, because when I travel through this particular branch, then I can learn something from it, or else there are different kinds of attributes and they are not similar. So, and there is a lot of uncertainty and surprises as I keep traveling. So similarly with this particular node, here when I travel for entropy of A, it is split after B, and here we see A and A. So but again it is getting repeated over here. Only the entropy here is B is actually new over here. So I get to learn that B is there over here. So I can actually write it simply as minus 1, 2, 3, 4, minus 1 by 4 here, and when I travel here from here I can write it as minus 3 by 4 here. So the entropy for A would be minus 3 by 4 log 3 by 4 and minus 1 by 4 log 1 by 4. So this is how I can write it for to explain you how Pi log Pi, that is for entropy. And another example which I can give you using the categorical data sets or any feature data sets is for example, if I have the target feature as it will have rainfall today. So if it will have rainfall today, the other attributes could be some other attributes like the place I'm going to go or the dress I'm going to wear, something like that. That is actually a classic problem for Bayes algorithm or the naive Bayes algorithm. So so for information gain also, if I want to explain, then I have to take a data set. So the statistical formula for information gain is entropy of, say I want information gain of A comma B, and where I already know I have calculated the entropy of A. I have already visited this parent node A. Then I for information gain of A comma B, I can write it like entropy of A minus sigma mod of SB by SA and information entropy of A comma B. Okay, so I have actually written a statistical formula here because when you're actually calculating the information gain, we want to see like information gain is calculated, or it is actually a specific estimated in the C4.5 and the Id3 algorithm, because you know in the information gain, every time when we travel through a branch, like previously we were traveling to the A branch, B branch, I had A as the grandparent node and P as the parent node. So you can actually learn something through a left node, and when I was traveling to the right node, then I got it as minus 1.4, like that. There might be very big decision trees, or decision trees which have a depth of 104 or 1 million terabytes or gigabytes, because usually machine learning algorithms, they mostly run on big data sets. So the by the depth I mean the number of branches or the number of levels, like that, for the decision tree. So in that particular in that particular scenario, information gain, if we calculate, then we get to know like based upon the number of samples which are below the children node, then how important it is to travel that particular branch. So at the parent node, then we usually have information gain. It is a probability value which lies between 0 and 1. And see, for example, if I want to if I take a data set where it will rain, yes, no, yes, no, okay, it will rain is my target label. Let's take a small one here. I have lesser space here. Okay, this is my target label. Okay, and it will rain or not, and the climate on that particular day. Say it is snowy, summer, cloudy. Okay, I have taken 3 attributes, so you can read it as: when it is snowy, then there's a probability that it might rain. When it is summer, then the probability of rain is not there. And when it is cloudy, then it might rain. Yes. So this is the target label, and this is my attribute feature label. Okay. So, and this is my entropy A, that is a target A value, and this is my B value. So if I want to calculate entropy of A, that is rain, it will be like I have yes and no. How many yes do I have? 2. How many no do I have? 1. So you can actually write it as minus 2 by 3 log 2 by 3 minus 1 by 3 log 1 by 3, because entropy actually is minus pi sigma log pi. Pi will go inside. So this is actually how the entropy for rain. So I do not have a scientific calculator here now, but usually when you have scientific calculators in class, then it is actually calculated that like that. So for entropy of climate, so if I want to calculate information gain now, I was explaining information gain of rain, comma, climate is equal to, so when you are calculating information gain, then I'll write a small table here so that you can see this will become very low here. So I want to calculate for information gain of rain, comma, climate. So for climate, if I take it as snowy, summer and cloudy, and yes or no. Is snowy, how many times it's coming? 1 time. No is 0. Then again for summer it is coming no 1 time. Summer no. Cloudy, yes 1 time. 0 no. So you have to draw a table like this. a machine learning algorithm in the backend, it draws tables for this, like not tables, but it directly sees your algorithm, and it is automated algorithm, so it will directly tell you the proportions. But now I'm manually doing it for you. So if I want to calculate information gain here, then I already have this particular value, so it will be EA of rain minus so what will be the output here? 1 1 1, it is 3, so it will be something like minus 1 by 3 log 1 by 3, then again everything is into 3. So it will look something like this, your information gain of rain comma climate. So that is how the information gain is calculated. Like that, the person will be able to see if it will rain or not, and on which day, on like on which climate. It will actually give you the probability, like how probable it is for it to rain. And simply suppose if I want to draw the decision tree for this particular problem, then you can also draw it. Like for example, for climate, you can say when it is snowy, this is no and this is yes. Snowy, then you will not be able to see here if I draw, but usually where should I draw here? Should make some space. That's the reason I have actually purchased a board, so that I can write it every time, or when I'm explaining any algorithms, I'll be able to write it. Usually in PowerPoint presentations, if you keep editing it, then you have to make a lot of editing in Microsoft Paint. So suppose if it is going to rain, right? So this is yes, this is no. So everything which falls on the right side is yes. So this is my climate. This is my climate. This is my rain attribute. So when will it not rain? When it is summer. When will it rain? When it is snowy, and when it is cloudy. So because I want to see when will it rain, yes or no, then you have to actually calculate the entropy here. Then again you have to calculate entropy here, entropy here. So where will I get the information gain? I will get it at wherever more than 1 or 2 nodes are there. Over here I'll get I of rain comma climate. I get to see information gain over here. So like that, if I have more than 4 or 5 attributes, then the machine learning algorithm actually decides like which branch should I travel and which particular column is important using the information gain. And the Gini index is actually used in the CART algorithm mostly. So in the CART algorithm, it is actually gives you the ratio of the impurity and the misclassified outputs. Like for example, if I have if I wanted to see one of my grandparents alive, but my grandparent was dead in the hospital till I went. I know it's a bad example, but can't help it, sorry. Okay, I'll give you another example. Suppose if I wanted to see a tree which is blooming very nicely, but there was a hailstorm and the tree actually in Tufan it went off, okay? And so the misclassified output will be somewhere between between 0.0 to 1. So similar to entropy, in this Gini index also you have values like between 0 to 1, and it is a probability of misclassified ratios, and here it is, you can say, the purity ratio. And Gini index ratio, it is very well the Gini index and the Gini impurity, also you can say Gini entropy or Gini ratio. So like that you can say. So this works excellently on big data sets, and it is used for classification as well as regression in the CART algorithm. And you can also give like -1 minus pi whole square. So this is a probability and this is a linear function. And in this particular algorithm, it is not logarithmic like the entropy or the information gain, because in here you have lesser computations like when compared to the normal decision trees, and the computation is actually fast. And suppose if I have a very big bulk tree, like I have something like this is actually a forest. Yeah. And so I have a small decision tree over here. So how should I know which node should I travel? I should travel this side or this side or this side. So usually machine learning algorithm, suppose I'm machine learning algorithm, then I'm going to pick this side randomly. I'm going to see what is the misclassified ratio. And at that point, if the actual value was somewhere between A and here also the value is A, then I will not travel that node. Or if here the values for this Gini ratio is somewhere between like it is very different, and the actual values are also same, and then there is misclassified ratio is very high, and I'll be traveling this because I want to see and learn about this algorithm. Okay, so that is our Gini indexing ratio. I'll give you an example of this Gini ratio because numbers work very well with algorithms. Yes, if I have numbers, then I'll be able to explain algorithms very well. If you have to solve problems, then you actually remember that particular algorithm for a lot of days. Say for example, I'm going on a trip, okay, and actually I have visited Sikkim, Manipal, Tripura, Bengal, Kolkata, and I have not visited Karnataka, Hubble, Matali, and tell me some more areas. Belandur, okay, and in Telangana state, if I say I have not visited Hyderabad, Nalgonda, Warangal, and in Maharashtra, suppose if I am not visited Thane, Pune, and what else are there in Maharashtra? Guys, comment down in the comments below. I don't know, yeah, more places. So suppose if I want to calculate, this is actually a directed acyclic graph, you can say indirected acyclic graph. So whenever there is arrows, you can say it is directed towards this particular side, and you can actually see that here I have visited these places and not visited these places. And for calculating the Gini index, I can tell you like when machine learning algorithms is there. Suppose I see that these particular places which are there are visited, and over here the Gini index, if I take it like Tripura, and if I take the location as Tripura here, okay, then the IG over here will be and if I give you a score, like if I want to visit it again, probability then 0, 0, 1, maybe 0.75, and all for everywhere for not visited, the probability will be greater than 0.25 to 0.5 over here probability. Then I can actually give you like IG of not visited is equal to 1 minus sigma of all these probabilities. Like if I give you Habal for Karnataka, Bangalore, if I give you somewhere between 0.3, Hyderabad 0.7, no, I should actually give you 0.1 and 0.25. If I give you for Karnataka, then it would be somewhere between 0.3 whole square plus 0.1 whole square plus 0.25 whole square. So whatever value is over here for not visited, it will be there. So somewhere if I say it will be between 0.25 whole square, then probability of not visited going places is 0.5. So like that, every time the for Gini index ratio, it tells you how many are misclassified. And suppose if I say what is IG on not visited node for say Telangana state, Nalgonda. If I asked you for Telangana state, Nalgonda, and the actual probability over here is 0.1, but if I predict a probability like somewhere between 0.75, then the information gain will actually tell you like 1 minus 0.1 whole square, that is actually some value like 0.009, like that. So it will actually tell see if like if I pick it from here, like what is the probability over at that point it is not visited, or like what was the value there, it is misclassified or not. So that particular advantage is there. So why should we choose Gini index when we already have entropy and it was there, it was invented? Then there are some actual computational advantages why CART algorithm is very famous, and it is automated algorithm. And the computational power when we use for Gini index is actually linear, and it is very fast, and it gives you very accurate values. It works for regression as well as classification, the Gini index. And entropy works only for classification algorithms, and it is logarithmic, and every time you want to check the purity ratio, then you have to actually calculate the purity for most of the nodes, or you have to check the purity levels for most of the branches, and same goes with information gain. And what else, Gini index can actually work on missing values, on outliers as well. So I have solved some problems for you, as well as I've also explained Gini index and entropy and information gain. Okay. ఏంది స్టాప్ అవుతలేదు.